into is the special senses. Up to this point in time, all right, dealing with this nervous system. I know, let's see, how many chapters now? 12, 13, 14, 15, 16. So 5 chapters now? Yeah. We have learned that we have that innervation to our skeletal muscles, the one that's relatively simple and easy, all right? We have learned that we've got this autonomic division. We've learned we've got the central nervous system, peripheral nervous system. We've got this sympathetic, parasympathetic. We've got this innervation to this, everywhere, innervated. But we have these senses that we're going to term special senses, and the reason for that, they're going to be special because the receptors, the makeup of their structure is going to be special. They're located in the head, and that's where they work. All right? We're not looking at them working anywhere else in the body except for that little bit of the equilibrium. Okay? So the special senses, yes, they are going to be special for a reason. One of the biggest is their receptors. The receptors that they have to detect their stimuli are very unique in their design. So their makeup is unlike stuff that we've seen so far. When we have a sense organ, this is where we're combining nervous tissue with other tissues and enhance the response to a stimulus. Our special senses, sight, smell, taste, hearing, equilibrium. All of them are going to be very interesting in how they function and how they are sent to their areas of the brain to be integrated and understood. Okay, it's a really interesting process. So we're going to see, just like in other stimuli that we receive throughout the rest of the body, okay, we're going to find we're going to have a stimulus, but now with the special senses, they have to carry out transduction. They have to change one type of energy to another. What? What does that mean?
I guess take the ears and take the vibrations and turn it into, I guess, electrical impulses that the brain can translate, I suppose.
They're going to have to take the stuff that comes to us on the waves of the air, okay, and then turn it into something chemical, which could become the electrical. For sight, we've got to take light, photons, and turn it into something chemical. For taste, hearing, all these special senses, we're going to have to turn one form of energy into another. And it has to become something chemical because that's what our body understands. Our body understands those little ions. So we're going to have to take the energy and change it. The potential of the receptor becomes important. For some of our special senses, it is only going to take a small amount of a stimulus to create the transmission of that information. All right, it's not going to have anything huge. It can be something very small to make the impulse occur. And in some cases, when we become aware of one of these stimuli, for example, smell. All right, let's say you go to the department store, you walk through the doors that are right there at the perfume counters, you walk in and it's like, whoa, okay, wow. But by the time you get past it, it's not quite as strong anymore, to a point where you're not even noticing it. We're going to have subjective awareness. These senses are going to have the ability to adapt, and sometimes adapt rather quickly, and basically stop paying attention to the stimulus, which is kind of interesting, I think. So now, if we take a peek at looking at what we know so far, the general senses, and then do a comparison to the special, kind of gives us an idea of the differences that we're going to see. In the general senses, the sense of touch, okay? What do you kind of notice about these neurons? Structure is kind of like what we're used to seeing. And one neuron is feeding a huge area of the body. In this case, the skin. That's showing us what can happen with a general sensation of touch to our back. One neuron is feeding a huge area. Do we need to have a lot of information come from our back? No. But look at our fingers. Why do we need to have more neurons for fingers than we do the back?
Is it like a what is it, like a safety mechanism? So because we use our hands a lot more, we need to be able to detect different type of feelings, like hot versus cold, and sharp versus soft. And
We do. Our hands, if you think about the amount of space that they take up in the cortex to, take in all of that information, our hands, believe it or not, are taking in a ton of information. We have the ability to determine and pick up one piece of paper, or we have that ability to pick up all of it. We have the ability to touch something, know if it's smooth, if it's rough, the pain, the pressure, all of that. So it takes more neurons. So in thinking about that general sensation, the general sensation does have where it's just like, oh, okay, it's there. I'm not really going to pay a whole lot of attention to it. Or we have something very fine-tuned, like that of our hands. Well, we're going to find that the modality, the picking up of that stimulus, okay, and where it's going to end in the brain is now going to be a little bit different. Because up to this point, we've learned, based on the general senses, pretty much everything just going into the spine, getting taken care of in the spine, or making its way to the brain, that sort of thing. Now, we're going to see that the signals are going to have areas of the brain they're going to end at. For example, sight. Where is sight going to end? the occipital lobe. Here to here, basically. Okay? So, general senses that we have pretty much learned about to this point, they give us a good idea. But now we've got to we're going to see where everything's pretty much staying in the head region. We're going to find that for some of our stimuli, intensity affects how we perceive it, how the brain is going to integrate it. Intensity, something such as loud versus soft, think about hearing, okay? Bright versus dim, think about your sight. Strong smell, no smell. They're going to have, this intensity is going to affect the firing of those neurons. So those neurons are going to be affected by how much is present, how much stimulus is present. Duration. Okay, right now, as you're sitting here, how many of you notice the pressure of the chair? Did you notice it or think about it until I said something? Okay, when I said something, you were probably became aware of that pressure, okay? That's because the body has this wonderful ability to adapt to certain stimuli. We know it's happening, but we don't have to pay 100% attention to it. Same thing with special senses. Well, yeah, they're going to be, okay, yeah, they're going to, based on the duration, okay, it can actually make the neurons slow their firing. So the the length of time that you're exposed to a stimulus can actually make that neuron decrease firing, stop passing the transmission of the information. When we receive a stimulus, we're going to say that, that these receptors, ones that will pick up this huge burst of something, like, I don't know, a really loud car going by, okay? That would be a phasic receptor. So something that happens in a huge burst, the body recognizes it and then goes, okay, I'm done. Like, for example, how many of you wear perfume or cologne? All right. When you first put it on, you smell it, right? And then what? Nothing. It's like, oh, until somebody else might go, oh man, what's the perfume you're wearing? What's the cologne you're wearing? What? It smells so good. You know, and you're thinking, oh. Your body adapted to it quick and said, I don't need to fire that information anymore. Now, a tonic receptor. Pain. Do you like it? Do you have it? No? Yeah, okay. Wait, get to be my age, it's a daily thing, all right? For example, knees. Y'all know anybody that might have constant pain in their knees?